Hello and welcome back to the channel Understanding.Concepts.Of.Physics. In case you haven't subscribed my channel yet, just please subscribe this channel in order to follow future updates. In the previous class we had started with a thermodynamics introductory part, and we had done some topics, some definitions in it. We are going to just move forward with the same topic, and we'll proceed with something called as the first law of thermodynamics. So this is the first topic we are going to discuss today. Then we are also going to discuss types of variables, what kind of variables do we encounter in thermodynamics, and we'll also discuss about types of equilibrium, like what kind of equilibriums do we have. So basically we are going to discuss in this video these three parts. Let's quickly start with the video. Okay, so now here we are with the first law of thermodynamics. Now first law of thermodynamics, in many books you will find out that it is also called as the conservation of energy. The basic law of conservation of energy is basically called as first law of thermodynamics. Now if you remember the conservation of energy, which you might have learned in very early grades of your educational career, is that energy cannot be created, cannot be destroyed, and it can be converted from one form to another, and the total energy in the universe is kept constant, is constant. So this is what the law of conservation of energy is. The first law of thermodynamics is also basically the similar one, but just they have stated in a different form. It says that the amount of heat energy which is given to a system is equal to the change in internal energy and the amount of work done. So if you learn that in a equation, you can just see in the equation, the amount of heat energy given to a system is equal to the change in its internal energy plus the amount of work done. So dq is basically heat energy, du is the internal energy, the change in internal energy, and dw is the work done. So let's basically understand what this is. So I am again repeating, the amount of heat energy given to a system is equal to the change in its internal energy and the amount of work done. So whenever you supply energy, let's say in this diagram, if you are able to see this diagram, there is this container, and this container is fixed with a piston, and this is a burner. So we have put a burner on here so that it gets heated up. So as the burner is heating the container, the molecules and the atoms present in the gas which is present inside this container will gain velocity. As we have learned that the RMS velocity depends on the square root of temperature. So if the temperature increases, thus RMS velocity would increase. As CRMS would increase, that is the velocity, as the velocity increases, the kinetic energy would increase, and as the kinetic energy increases, I can say that internal energy would increase. Now internal energy is written as U, so there will be some change in internal energy. So as you supply heat, that is dq amount of heat energy, some infinitesimal amount of heat energy, there will be change in the internal energy du, and definitely as the temperature in this container will rise, there will be development of pressure, as pressure is going to exert on all the walls, on this wall, these side walls, on the bottom as well. But the three walls are fixed, they are not going to move, they are immovable. But however, this piston is a movable arm. So as the pressure is acting on this walls of the piston, this piston is going to move up. Now this is going to move up because pressure is equal to force upon area. So the amount of force exerted on this wall divided by its area, force upon area, that will be giving this pressure. So that pressure will make this wall move up. So now if I just want to draw it like this, then it would look something like this. The piston is going to move up, and now the gas molecules will be having a larger amount of energy, so the larger amount of volume. So because the piston was earlier at this point and now the piston is at this point, you will find out that there is some displacement, and there is force acting on it. So if you see, force is equal to work done is equal to force into displacement. So because for work done is equal to force into displacement, you will find out that the piston is going to move up, and this equation will get valid, that whenever you give some amount of energy, whenever you give some amount of energy, the energy will increase its internal energy, or and then dW is the amount of work done on the system. Now if you just if I just redo it, now just copy this. Okay, now just watch this. In case if I do not hit this, and if I kept into a bath of ice, let's say I'm just keeping this near ice, so I'm placing ice around here, around this, so I'm just trying to cool this. Now what is going to happen? The heat is going to flow from the system to the ice, and ice is going to melt. Definitely we are not focusing on ice, that will become a surrounding. However, the inside part, that is this part, is our system. Now system is going to cool down. As the system is going to cool down, the temperature is going to come down. So as the temperature reduces, CRMS reduces, that is the velocity reduces. As CRMS reduces, the kinetic energy reduces. As the kinetic energy reduces, the internal energy also reduces, which is written as U. So the internal energy would reduce, and the piston, which was earlier at this point, now the piston might move slightly down, and because the piston is moving down, you will see there is some force, there is some pressure acting on it. And now here, the reason why the piston is moving down is because the pressure inside is reduced. However, the pressure outside is the same. The atmospheric pressure present outside is pushing the piston down, so the piston is going to move down. And again, if there is force, if there is displacement, there will be work. So whenever you supply energy, or you take energy out of the equation, out of the system, then this equation is going to get valid. So amount of energy given or taken is equal to the change in internal energy and the amount of work done. So you see, this is the explanation of first law of thermodynamics. However, we can just pull it over in three cases. Okay, let's say, okay, suppose if I have case 1 wherein the internal energy is greater than 0. So if this number is greater than 0, I can just move this equation like this. Maybe I will just write it like this. Du is equal to dq minus dw. So I just move that dw, this dw on the other side. So what do I get? And suppose in the first case I am saying that if du is greater than 0, so if this number is greater than 0, that means this number dq has to be greater and this number has to be smaller. Only then we can get du as positive number. So du is greater than 0, then dq would be greater than dw. Now that way you can just have different kinds of permutations. So du would be less than 0. Suppose if the du comes out to be less than 0, so if I just move this on the other side, I'll again get the same thing. Du is equal to dq minus dw. So if this comes out to be a negative number, definitely dq should be smaller and dw should be a bigger number. So smaller number minus bigger number, you'll get a negative number. So this is the second case. And the last case, if du is equal to 0. So now if the du itself is 0, like if du itself is 0, then you can say that dq is equal to dw. That is, the amount of energy supplied or taken is equal to the change in kinetic energy, and this is only going to happen in a very special kind of process which we call as isothermal process. Now more on processes as we go forward in this particular chapter. Isothermal process is a process in which the temperature is kept constant. So when the temperature is kept constant, the velocity would remain constant. As the velocity would remain constant, the kinetic energy would remain constant. As the kinetic energy remains constant, internal energy remains constant. So in an isothermal process, if the internal energy is constant, then the change in internal energy is 0. This is a very nice MCQ. People may ask you that Okay, work done is equal to the change in energy, and this will happen in which process? It will happen only in isothermal process. So this is all about first law of thermodynamics. I was supposed to do all the three um, topics, but I am seeing that the video has become longer. First law of thermodynamics demanded that kind of attention, so I'm going to stop the video at this point, and I'll club the other two topics in my coming video. Thank you so much. In case you have not subscribed, just do it, and keep following the videos to understand more about thermodynamics. Thank you so much. Bye.